Hello, Honors Algebra 2 Trig students. This notes video is about modeling with exponential functions. There's a base version of the exponential function, and that is right here, the y equals a times b to the power of x. And when you consider what the meaning of each of these two things are, a is the initial value, and that's because when you make the x zero, or you often we say that maybe the time being zero, that would give you b to the zeroth, which is one. So you would just have a being the value of y. So that's why we call it the initial value. Where b is the growth factor. It's the number that keeps getting multiplied in by a, however x many times is there. So for example, if we had y equals a b to the fifth, that means this factor b would be multiplied by the original value a 5 times. So it would have gone through this series of growth 5 times. If the growth factor is greater than 1, we have exponential growth. And when the growth factor is less than 1, we have exponential decay. So things keep getting smaller and smaller, which makes sense, because if you say I had 100 times 2 to the fifth, every time you'd multiply 2 in, it would make 100 get bigger. And if you had, say, 100 times 1/2 to the x value, every time that x gets bigger, you'd multiply by another factor of 1/2, and then we keep having how much of 100 is there. We have other ways of writing this. We could write y equals a, either 1 plus r or 1 minus r to the t. This is just basically another way of writing b, where r is either a growth rate or a growth factor. So if we say something grows by 10%, or actually let's go instead with 12% per year, you'd have 1 plus 12%, which is 0.12 to the power of t. This would model something growing by 12% per year. If you had it decaying or losing, say, 15% per year, it would be a 1 minus 0.15 to the t, because when you multiply this in, it would take away 15% each time from a, or from whatever value you currently have. Now, here in this function, y equals 10 times 0.4 to the power x, this is an exponential decay. The reason we know it's an exponential decay is because the b value is less than 1. There is a 60% loss each time. Because we're losing 60%, we're only keeping 40% of what's left over every single time. Where this here is an exponential growth. We have an initial value of 2. And actually, sorry, I should have said the other one had an initial value of 10. And it's growing at a rate of 0.015, or 1.5%. Now, understanding these equations allows us to work with application problems that involve exponential growth and exponential decay. And here we have this problem that the half-life of a medication is the time that it takes for half of the drug to be eliminated from the body. The half-life of Advil is represented by this equation. Now, this equation looks slightly different because it is the t over 2 power. And what that means is that it takes 2 hours for the growth factor to go ahead and to place. And so every uh, even number of hours, it gets halved. For example, at the second hour, when t becomes 2, you have 2 over 2. It's one time of this 0.5 being multiplied in. At t equals 4, 4 divided by 2 is 2. It would be 2 times of this 1/2 being multiplied in. M is the initial dosage and T is in hours. We have a 200 milligram dosage of Advil is taken at 1 p.m. How many milligrams of the medication will remain in the body at 6 p.m.? Well, time 0 is 1 p.m. We're going to go ahead and look at this as R, the remaining amount of the Advil, equals 200. And then we have 0.5. 6 is 5 hours after 1, so you have 5 halves here. So we could take out a calculator and use the calculator in this situation to substitute this value in, and we're going to get an exact amount that would be remaining. So we had 200 times 0.5 to the power of 5 halves. So we get 35.355 milligrams. So at 6 p.m., there's 35.355. I'm going to double check that on the calculator. Milligrams of Advil remaining. So we have another example here about depreciation. Your new computer cost $1,500 originally, but we're losing 18% of its value every single year. We're going to write an equation that would compute the value of the computer at X years in. So let's make Y the current value. It started at 1,500. It's going to lose 18% of its value every year. So that means that this is 0.82 n to the power of x. I got this 0.82 by doing 1 minus 0.18. That is the 0.82. We could use this to determine how much the computer will be valued in 6 years by just making x 6. So we have 1,500 times, that's 15,000, 1,500 times 0.82 to the power of 6. So that says that computer is now worth $456.01. How long will it take for your computer to be worth to close to $0 according to your equation? Well, this is an exponential equation. So it would never be able to become 0, because no matter how many times you multiply 0.82 in, you're always going to have some amount of value. For example, if you had 1,500 times 0.82 to the power of 100, that means a century would have gone by, and it does have pretty much 0 for value because but it's a positive number still. It's just positive 3.6 e negative 6, which would mean uh, 3.6, and then with the decimal place moved over this way 6 times, so it'd be 0.0000 1, 2, 3, 4, 5 dollars, which is just a fraction of a penny. So we had to find something that maybe we want to consider a value that would be close to $0. I would say when it's worth 1 cent, it would be worth close to $0. So Although it's not possible to be actually exactly worth $0, we can figure out when it's worth 1 cent, and that's close to $0. So let's go ahead and consider our equation. We have y to be 0.01, and we have 1500, 0.82 to the power of x. Now we can solve this. Well, we're solving an exponential equation. We've done a lot of this lately. We can divide both sides by 1500, and we get 0.82 to the power of x. Well, the best way to write something like this is to move it into log form. So we have log base 0.82 of 0.01 divided by 1500 is x. This is the power it takes to go from 0.82 to get that expression. And well, we can plug that into our calculator. Math, log base, we have 0.82. The argument is 0.01 divided by 1500. It would be 60.06 years until the computer would be valued at 1 penny. So x equals 60.06 years before the computer is worth 1 cent. We'll save the rest of this for our video part 2.